So, what are molecules? Well, they're two or more atoms held together. Now, you can have molecules that have the same or different elements held together, generally by interactions among their outermost electron shells. Compounds are a little bit more specific. They have to contain different elements held together. So, for example, H2O, water, that's an example of a compound. It's also an example of a molecule, because that is a more general term for two or more atoms held together. A molecule that is not a compound, though, would be oxygen, specifically oxygen gas. That's two oxygen atoms held together. Now, those are the same element, so they don't fit the definition of a compound, which is molecules composed of different elements. So, we're going to talk about these interactions that form molecules. They're attractive forces, and whether or not atoms gain, lose, or share electrons, they're one of these three major types of chemical bond. Those types are an ionic bond, where we form ions by transferring electrons, covalent bonds, where we share electrons, and hydrogen bonds that are a little different from ionic and covalent bonds, where we actually see attractive forces between separate molecules. Let's talk about ionic bonds first. So, most ionic bonds fall into the category of salts, and when you dissolve salts in water, their ions, their charged atoms, separate out, but we would still see their attractive positive and negative forces. With ionic bonds, we're going to be seeing a transfer of one or more electrons. That results in a charged atom. Again, that's what we're calling an ion, a charged atom. One of the ions will be an anion. That's because that one has a negative charge, because it will have accepted or gained an electron, making it overall more negative. One of the other ions will become a cation. It'll have a positive charge because it will, instead of accepting an electron, have donated an electron. So when you talk about ionic bonds between at least two atoms, you're going to be looking at an electron acceptor and an electron donor. And that's going to disrupt the neutral charge of neutral atoms where the protons and electrons were once balanced out. Once you have charged ions where one is positive and one is negative, you have an attraction between those opposite charges. That actually results in an ionic bond. That's why salts are held together in a desiccated or dry state, but oftentimes do separate when dissolved in water. So here's an example. We're going to see the formation of sodium and chloride ions. Let's start on the left. You have a sodium atom that has one electron in its outermost shell. Well, it would like 8 electrons in its outermost shell, and it's a lot easier to get rid of one electron than gain 7 more. So if it donates that electron to chlorine, then it's going to be able to have 8 electrons in its second orbital, which becomes its outermost shell. So that makes sodium a happy, stable atom. Now, that electron that's donated by sodium goes to chlorine. It actually helps it satisfy that octet rule as well, because chlorine only has 7 electrons in its outermost shell, and it's way easier to get 1 electron added to that shell than to, say, get rid of 7 electrons in that outermost shell. So with this exchange, this transfer of electrons, both atoms, sodium and now chloride, become stable. But sodium donated an electron, so now it's more positive. And chloride, now called chloride, gained that electron. And so now it has a slightly negative charge. And when they're together, this positive and negative ion are attracted to each other, creating a crystalline structure generally based on that attraction. And that forms generally or usually a salt. Now let's look at covalent bonds. Covalent bonds are formed by the sharing of 2 or more valent shell electrons. So that's different from ionic bonds. Ionic bonds transfer electrons, covalent bonds share electrons. And you can share more than one pair of electrons. If you share one pair, that's 2 electrons, and that's a single bond. If you share 2 pairs, that's 4 electrons shared, and that's a double bond. If you share 3 pairs, that's a triple bond, and that's 6 electrons shared. The reason that we share electrons to form covalent bonds is so atoms can fill their valence shell and qualify or basically fit that octet rule. where except for that first orbital, all valence shells would like at least 8 electrons. There's actually two different types of covalent bonds, polar covalent and nonpolar covalent bonds. So let's look at a couple of examples. Here we have hydrogen forming single bonds with one carbon. You can see that each hydrogen shares 2 electrons, so one pair of electron, and the structural formula is drawn as a single line for that attachment. So that represents a single bond. If you share electrons, you get to count those electrons for both atoms. So each hydrogen atom here in the resulting molecule now has 2 electrons, and we would count all of those shared electrons, including the ones that carbon originally had in the outermost shell, for carbon. So it has 8 electrons in its outermost shell. Here we have 4 electrons shared between 2 oxygen molecules, and once shared, that is going to satisfy the octet rule for these oxygen molecules. So we get to count the 4 in the middle and the one up top, the bottom, and the 2 at the left for the left oxygen, and similarly the right oxygen. That gives both oxygens 8 electrons in their outermost shell. Because they're sharing 2 pairs of electrons in the structural formula, we use 2 lines to show a double bond. And here we have 6 electrons and 3 pairs of electrons being shared to make sure both nitrogens have 8 electrons in their octet in that outermost valence shell. And that's going to be depicted in a structural formula using 3 lines. That's a triple bond. When it comes to the two types of covalent molecules, it really has to do a lot with what attracts the electrons the most and the size of the atoms. With nonpolar covalent bonds, we tend to see the atoms be about the same size, meaning they have about the same size of positive charges in the nucleus, or about the same amount of positive charges in the nucleus, and they're going to equally attract those electrons, and so they'll spend most of their time in the middle of those two atoms or molecules. With polar covalent bonds, usually we're seeing one atom or multiple be much bigger than some of the other atoms that participate in this polar covalent bonding. So they're going to have more positive charges in their nucleus that attract those electrons more often than not. And if we were to freeze time, we would see that those electrons spend much more time near the bigger, more positive atom. So we have equal sharing of electrons that forms nonpolar covalent molecules, and unequal sharing of electrons that forms polar covalent molecules. Nonpolar covalent molecules are equally sharing electrons, and you're more likely to find those electrons about equidistance from the nucleus of each of the atoms sharing that pair. Whereas with a polar covalent molecule, you're actually going to create poles or two different sides that behave slightly differently in that molecule. The oxygen side of this molecule is going to be slightly negative because it has a larger positive nucleus because of the more abundant positive charges or protons in that nucleus. And so it's going to attract or have a stronger pull on those electrons, and so they'll spend more time near the nucleus with the larger charge, so oxygen. So if we were to freeze time, most of the electrons would be near oxygen, making it slightly negative on the whole. Whereas hydrogen's much smaller, less protons in the nucleus, so they exert a much smaller or weaker pull on those electrons, and so they're going to be considered slightly positive. They don't hold on to as much force with those shared electrons. And hydrogen bonds depend on positive covalent bonding. Looking at polar molecules like water, we can very easily examine what a hydrogen bond looks like. With a hydrogen bond, you're going to have the partially positive hydrogen atom of one molecule, in this case a water molecule, and it'll be attracted either to an oxygen or nitrogen of another molecule. If we use two water molecules, it would be attracted to the negative, slightly negative, oxygen atom of another water molecule. This actually gives water really unique properties like cohesion and adhesion. It makes these hydrogen bonds, while comparatively weak by themselves, collectively or altogether, very strong. So here we see dotted lines. Those are hydrogen bonds. They are between the slightly negative oxygens and the slightly positive hydrogens of differing water molecules. So these are not between atoms or elements, they're between molecules. That's going to make hydrogen bonds a little bit different from covalent or ionic bonds. So here's a quick review. These are just different common types of bonds in biological molecules, including ionic, covalent, and hydrogen. Again, the key word for ionic is transfer of electrons, creating two ions, one positive cation and one negative anion. With covalent bonds, we're going to share electrons equally, it's nonpolar, unequally, it's polar. We saw two examples, hydrogen gas for the nonpolar covalent bond and water for the polar covalent bond. And hydrogen bonding happens between hydrogen and a nearby oxygen and nitrogen, and we looked at an example between two water molecules. And by themselves, hydrogen bonds are definitely the weakest, with ionic bonds being slightly weaker than covalent bonds, but hydrogen bonds collectively can be quite strong. And that gives water properties again like cohesion, where water molecules are going to stick to each other, and adhesion, where water molecules tend to stick to other things. So that produces things like surface tension, high heat of vaporization, many other characteristics that we're going to look at in the next part of this PowerPoint.